Good evening. My name is Jack Wild, and this is my take on community problem number 3. All right, so the two questions in this community problem are taken from two different modules, so there's not a lot of connective tissue here. The first question looks at the use of L'Hopital's rule to evaluate limits of functions at improbable values like infinity, and the second question touches on some new vocabulary we're learning to talk about specific points on a curve. But it's structured like an art project, hence the Portlandia themed presentation. Okay, so the questions in part 1 of the problem are all about figuring out which function is dominating which, and can be answered by asking if you get 0, infinity, or something in between when you divide one function by the other. As soon as we introduce the concept of infinity, it's important to understand that the equal sign stops meaning what it usually means. Instead of equals, think of it as might as well equal. Specifically, when you have two essentially limitless numbers and you divide one by the other, you don't actually get 0 or infinity. You get a value that might as well be 0 or infinity. So for example, if you divide a number by another number that's marginally larger, you would get a positive fraction, right? And the bigger the difference between the numerator and the denominator, the smaller the number you would get. So when we're working with infinity, even a marginal difference becomes, well, infinite. So that dividing that smaller number by the larger number might as well equal 0. And the same is true of the inverse. If I have a relatively stable number in the denominator and my numerator is getting even just a little bit bigger over time, when we get to infinity, you're essentially dividing the infinite by the finite, which may as well equal infinity. So with all of that in mind, we're going to sort of divide one function by another function, and if the result might as well equal 0, then we'll say that the function in the denominator is dominating. If it might as well equal infinity, we'll say the function in the numerator is dominating. If we get a constant, then we'll say that they're growing at the same rate. All right, part A. Which of these two functions dominates the other one? Let's start by taking the derivative of each of them. The derivative of a logarithm is just, well, it's just 1 over x, so that's easy. Square root of x takes a few more steps, but it's worth it. You'll see why in a second. Okay, yeah, the exponent rule. Yeah, good. Yeah, can't have an exponent in the denominator. Getting math. Yeah, this is a lot of work for one derivative. Still going. Still going. Okay, so I've written this a little bit funny, but there's a reason to this madness. Here we are with the derivative for both functions. I've written them this way for easy comparison because, again, the question we are trying to answer is which one of these derivatives is growing faster. So which is larger, 1 divided by x or 1 divided by x times something? Stop for just a second and think about that question. The only way 1 divided by x multiplied by something could be less than 1 divided by x is if that something is less than 1. All right, so can it be less than 1? Well, in this case, it can only be less than 1 when the square root of x is less than 2. But we're talking about what happens when we take x up to infinity. So no, the multiplier is never going to be less than 1. So what does that mean? Well, as x approaches infinity, the derivative of the square root of x is going to be infinitely greater than the derivative of log of x. In terms of a limit, which you remember is just the idea of a number that is being trended towards, not actually reached, we could say that dividing the log of x function by the square root of x function yields effectively a 0. So it is said to be, so the square root of x function is said to be dominating the log of x function. Part B asks us to make a generalization about the way these two kinds of functions work. The thing is, the n variable isn't actually relevant. We can take x to any root and we still end up asking the same question. Is 1 divided by x greater than or less than 1 divided by x times a number that will be greater than 1 before we get to infinity? The answer is always the same. 1 divided by x is going to be less. So If the logarithm function is in the numerator, then it's being dominated. Well, it's being dominated wherever it is. If it's in the numerator, we get a 0. If it's in the denominator, we'll get infinity. Part C wants an explanation as to why e to the x will always dominate a polynomial function. So the trick to this one is to just keep applying L'Hopital's rule until you wind up with a clear result. When you calculate the first derivative, you don't end up with equals 0 or equals infinity. Instead, you end up with, well, we'll just do the math here, sorry. Instead, you end up with infinity over infinity, which is what they call indeterminate. Another way is to say you're not finished. So the answer is still here, though, because what you'll surely have noticed, and what you probably already knew, is that the derivative of e to the x is always just e to the x. No matter how many layers of derivative we calculate on that function, the result will always be e to the x, which is actually what makes it e. A polynomial function, on the other hand, will be, I guess, reduced a little bit every time we calculate the next derivative. So at the first level, every exponent loses 1, every multiple becomes a constant, and every constant just disappears. That means that no matter how big and complex the polynomial, it will eventually reduce to 0. And the e to the x will not. So e to the x will always dominate a polynomial function. Part D wants a similar explanation as to why x to the n will always dominate logarithm x. So this one's pretty straightforward. If you recall, the first derivative of a log function is just 1 over the independent variable. So as x approaches infinity, you're dividing 1 by a larger and larger number, yielding a smaller and smaller result. The first derivative of an exponent function is doing the exact opposite. It's raising a larger and larger value of x to the n minus 1, then multiplying that by a positive integer. Again, you never actually get to infinity, but as you're raising the value of x higher and higher, the difference between these two numbers just gets bigger and bigger and bigger, so that effectively dividing one by the other just yields 0, which means the x to the n function is dominating. Now, just to be clear, we could flip the denominator and the numerator, and the result would change from 0 to infinity. But the conclusion about which one is dominating which, it would stay the same. It's always going to be the x to the n function. Finally, part E asks us to imagine two nonlinear functions where neither one of them is dominant. So what that means is that when we divide one function by the other, we should get something between 0 and infinity. Seems easy enough. Since polynomials reduce at a fixed rate, we can easily set up two equations that we can derive into a non-zero, non-infinite number. Now we'll divide one by the other. We'll just reduce it. You just keep applying L'Hopital's rule, and you get down to 6 over 72, which is a constant. I'm not a math guy. I think that's 1 over 12. So that concludes the part 1 of community problem number 3. Now part 2. So problem number 2 is taken from the 3rd module, and it's not my favorite. I hate the exercises that ask us to draw or guess what the drawing they've provided means. Invariably, the number I used to perform the calculation doesn't exactly match the number that the author used, so it turns into a question of my ability to visually estimate distances on a drawing. I hate guessing games, and I resent the fact that the author thinks their explanations are so good that they don't need visual aids that make sense. They aren't that good. This is the life we're living, right? So there are 4 parts to this problem. We're just going to power through it. This is the graph they've provided. As you can see, they've graphed the first derivative of the function that we'll be guessing about. We're meant to sketch a graph of the f of x and the second derivative of f of x in the graphs to the left and the right, respectively. We'll start with the graph of f prime of x. Okay, so the first thing we're asked to do is construct the derivative sign chart for f. This would be a walk in the park if they had also provided the formula, but since they didn't, we'll just eyeball it, which is exactly what you want to hear an engineer say. If we had the formula, the first thing we would do is identify the points where the derivative goes to 0, what they call the critical numbers. This is a graph of the derivative, so we'll take it that our critical numbers are here and here, -1 and 1. Next, we need to determine whether the derivative is positive or negative during each of the intervals. I'll admit that this is easier to do with a visual than with an equation, but it still grinds my gears. So the first interval, -2 to 1, the sign is negative. And what that means is that the value of f of x should be decreasing in that interval. The next interval, -1 to 1, the sign is positive. There's a turn in there, but the value is positive the whole time. That means that the value of f of x is increasing during that interval, although at a variable rate. The third interval, 1 to 2, the sign is still positive. So what do we know from this? We know that there are two critical numbers, -1 and 1, but only one of them represents a local extreme. At -1, the derivative goes from negative to positive, so the function must hit a local minimum, then start climbing again. The key here is, of course, the change in the derivative sign. All right, part B of this problem asks us to take the graph of the derivative and sketch a graph of the second derivative. I'm seeing two horizontal tangents, so we can say the second derivative will hit 0 at these points. That one on the right looks like a 1 to me. The one on the left, I don't know, -0.4 maybe. We can try to add a couple of tangent line guesses at other points that look like they intersect a point on the graph. -1.5 looks like it might have a slope of around 4. -1 looks very close to a slope of 2. 0 looks like a -2 slope. 1.5 might be a slope of 1. And 2 might be a slope of 5. Again, these are all just guesses, but what can we do but connect the dots, right? Yeah! All right, so now we'll construct a second derivative sign chart based on my awesome drawing. First, let's mark that -0.4 and the +1 as the critical numbers. That way we'll have our intervals and we'll be ready to go. The first and last intervals have a positive sign, indicating that the graph of f of x should be concave up during those intervals. The middle interval between -0.4 and 1, which incidentally are the inflection points, have a negative sign. So the graph of f of x should be concave down during that interval. There's only one thing left to do, which is graph function f of x. Brace yourselves. All right, so they do give us one starting point, which is f0 equals -1/2. So we'll start by drawing that on the graph. Based on the graph of f prime of x, we know that the tangent line at 0 should be at a slope of 1. Building to the right, we know that the concavity at this point is downward, and that we need to flip concavity at 1. So it should bend down to a flat line at 1. We don't know how high or how low it should be, but the first derivative doesn't have any wild swings in it, so I'm just keeping it as smooth as I can. And building to the right, then we go up. All right, so building to the left, we know that we have to flip the concavity at -0.4, but the graph should continue going down until -1, where it should start going back up. And pull that tangent line out. All right, so there we go. That's a rough estimate of a graph of the function of x, f of x. Seems consistent with the other two graphs, such as they are. So listen, that's my take on community problem number 3. Let me know if you see any problems with how I took on the questions. If you have any advice, thoughts, or ways to do it better, please let me know. Thank you for watching all the way through, and good night.